Hi and welcome to Statistics Video 1. Now, the statistics unit in Year 10 does have a tendency to change a bit, and some things are added in, some things are taken out, depending on your program for Year 11 and 12. So this might not actually be Video 1. But let's go with it anyway. I'm going to call it Video 1 Part 1. It's a subtopic of statistics which are really important for math methods, and that is sketching bivariate data. So it's basically scatter plots and leading into lines of regression and regression analysis and things like that. Be really important later on for math methods. So part 1 is sketching bivariate data, and in this video we're going to look at types of data and how we sketch categories, and also correlation, making some predictions. So let's do a couple of definitions first of all. So bivariate data versus univariate data. And bivariate data, which is probably where I'm going to aim my definition, bivariate data is data that has two linked variables. Whereas univariate data, well, univariate data doesn't have two linked variables. It's just a set of data as one single list. So for example, bivariate data might be comparing your height against your age, or maybe the number of cars that pass a certain traffic light over a certain amount of time. Whereas univariate data would just be if you went and asked somebody whether they preferred pizza or spaghetti bolognese for dinner. And that would just be collecting a single set of data that's not compared or linked to something else. And then I also need to talk to you about discrete versus continuous data. And before I do that, it's important to note here that these are both numerical data types. So when we talk about discrete and continuous, we're talking about numerical data. So don't get confused there with categorical data, which would be that eye color or favorite sports team or something like that. So discrete versus continuous, both can be used for a scatter plot, but it's important that you understand which is which because it can have a bearing on how you approach some of the questions later on, and more importantly, how you make predictions with that data. So the definition is that discrete data is countable, whereas continuous data is measurable. So what I mean by that is that discrete data is data that usually seems to be whole numbers only. So something you count. The number of students in a classroom, for example, maybe the number of chocolates you have in your fridge or something like that. So something that you get to 5 and then the next thing is 6. There's nothing in between. Whereas continuous data is measurable. So if you measure something, that'll mean it's a weight or it's a length or it's a time, then it is measurable and that will be continuous data. And it'll be important to notice that because depending on the data, it might have an effect on how you approach things. Now let's talk about correlation. So here I've got 3 graphs which I have borrowed from my biology website just to really reference what we're talking about. So in the first graph, we have a fairly strong positive correlation because it has a positive gradient. You see that light blue line is our prediction line, our trend line, or our regression line, and it has a positive correlation. The second graph might even be slightly stronger correlation, but in this case it's negative because it has a negative gradient. So it's going downwards, the blue line. I'd say that the coordinates are a little bit closer to the blue line than the first graph, so maybe slightly stronger. The third graph has no correlation. We can't predict where the next data point is going to end up because it's a bit all over the place. So it might have a really, really weak correlation one way or the other, but that'll be hard to use in predictions, and so we would probably steer clear of predicting with that data. In the next video, we'll talk about regression analysis, and regression analysis actually provides us a measure of the strength of the correlation, and we can use that as evidence. Rarely will you get a raw set of data that has perfect correlation, so you're always going to have some weakness in your model and in your prediction, but if you can get yourself a really good regression analysis that shows strong correlation, well then that reduces the weakness in your model. That's what you're aiming for. So there's correlation. What I'm going to do now is talk to you about how to sketch graphs and just some tips for sketching graphs. So I've got a little list there and I'm going to sketch a graph here and just make sure that we're right with that. And then we'll answer a couple of questions which involve making predictions from graphs. So here's some tips for sketching. There's my data. First of all, make sure that your graph, particularly in an exam or an assignment situation, make sure that your graph has axes labels and possibly a title as well. Definitely in an assessment situation. It depends a little bit on the context. So my x-axis here is time, and it's measured in weeks. So I'm defining my variable and I'm providing my unit. And my y-axis is height, and it's measured in centimeters. And again, I'm providing a unit in this case. Now the next step is to plan ahead. So this is the second step here. And I'm going to plan ahead by saying, well, I've got to go from 0, 0 up to 8, 27. Now my data is in order, so it's very easy for me to plan ahead, but you might have to look through your data and make sure that 27, for example, is actually the largest value. And you'll notice that I've gone on my scale up to 40 and up to 10, so that works. But also have a look at the questions, because my question says, what will the tree height be at 10 weeks? If I go back to my data, I'll see that I need to go not just to 8, which is what I have here, but up to 10. So you need to make sure that your graph incorporates not only the data, but potentially the question as well, unless the question is asking you to use a linear function to predict, or perhaps that 10 is so far outside of your domain that it's really hard to use it to predict. So you've really got to pick and choose there and be a bit careful. So the next thing is make sure that you've got arrows, numerical labels, and axes labels. We've done the axes labels. I've got numerical labels and I've got arrows. And you'll see that the fourth one says numerical labels do not need to include every number. And it's a bit of a frustration that I see a lot. And people waste a lot of time writing every number up to 40 on their axes. And technically, as long as you've got a decent grid, if you give me one number, I know the scale. I don't need any more than that. But realistically, you've probably set some sort of systematic pattern. So in this case, I've gone up in 5s. 5, 10, 15, 20. It's systematic. It's clear. I know what each line means. That's all I need. Now, the last thing says use crosses to denote the points. And it's really important here that the crosses are good. Crosses denote the finite point, the tiny little speck in the middle, but you can draw a cross big enough so it can be found by the person reading the graph. So I really strongly urge you to use crosses. A lot of technology uses dots though, and the technology can still apply the exact point whilst displaying a dot. So it can be done on technology. Crosses are better if you're drawing it. So I'm going to plot all these points. 0, 0 is here, 1, 3 is here, 2, 5 is here, 3, 9 is here, 4, 13 is here, 5, 15 is here, 6, 21 is here, 7, 24 is here, and 8, 27 is here. So there are all my points. And my questions say, when was the height of the tree 20 centimeters? And what will the tree height be at 10 weeks? Now, for questions like this, I really need to seriously consider a line of best fit, because all I've got here is a trend. Now this is raw data, so you might be able to say, well, when was it 20 centimeters, and map along this line here, which is a 20 centimeter line, and just find where it matches here, and I'd say, well, on that line segment, it's 20 centimeters after about 5.75, 5.8 weeks. But realistically, we should consider using a line of best fit, because that gives us a consistent solution that clearly indicates the pattern involved. So what I'm going to do is draw a straight line, one with an arrow, that represents my line of best fit, and I'm choosing to start at the 0, 0. Now you'll note here as well that I'm going to just do a couple of quick circles and show you. I've got 1, 2, 3 above, 1, 2, 3 below, and 1, 2 basically on the line. So my line of best fit here is reasonable and fairly representative of the data. 3 above, 3 below. I can see the data is quite snug around that line of best fit. Snug is the right word for it. And so we have a fairly good correlation. So the first thing is, when was the height of the tree 20 centimeters? So what I do now is I get another line, and I go from 20 centimeters and I find where it hits my line, which is here. And then I go from there down, and I find that it's actually predicting it'll be 20 centimeters in 6.2 weeks. So that's okay. We know that it's actually 21 centimeters in 6 weeks, so it's not quite right. But the general trend is giving about 6.2 weeks, which is good then, because if this thing grew again, this whatever it is that's growing, to a height of 20 centimeters, I would be able to predict about 6.2 weeks for that to happen based on the general trend. The second question was, what will the height of the tree be at 10 weeks? Well, let me just write down the answer to the first question. So at 10 weeks, I need to draw another line because I didn't actually make my line long enough. So let me just draw another line here, all the way out to 10 weeks, following the same line there. And now I can see that if I draw a line up from 10 weeks and then from that 10 weeks line across, it comes out about 33 centimeters. So we're looking at the answer of about 33 centimeters. Now, drawing these lines with my stylus on a computer is a little bit tricky, but you will have the benefit of a ruler and a piece of paper in front of you, which makes life a little bit easier. I've also got that time pressure that if I take too long, you will disappear from my video, and I don't want that to happen. So make sure that you do it neat and it's clear. The last note I want to make in this video is that I've done two different things here. This part is called an interpolation because I have predicted inside the data set. And the data set, by that I mean the domain, goes from 0 to 8. So any value from 0 to 8 is an interpolation. Whereas over here, I've done an extrapolation. An extrapolation is where you predict outside the data set. So I did an interpolation and then I did an extrapolation. Generally speaking, if you're asked to discuss your answer, interpolations are quite strong. Extrapolations can be quite weak. This one's not too bad because it's close to the data set. But the problem we have is we don't really know anything about what's happened here. So I know I'm pretty close to right in my interpolation, but my extrapolation, I don't know whether maybe at this point the plant has a growth spurt, or perhaps that's the highest it grows to and it stops growing. Whatever the context is, I'm saying a plant. So there's a discussion point for you, whether you're using interpolation or extrapolation. And so there you have it. Drawing scatter plots, using bivariate data, discussing correlation, doing a neat sketch, and then discussing the solutions to problems from that sketch. It's quite a hefty video, but some really important stuff moving into year 11 and 12. All the best.